Acid-base reactions are also called neutralization reactions. So before we can talk about the reaction, we have to talk about what acids and bases are. We've talked about acids a bit when we learned how to name them. Acids are substances that tend to form hydrogen ions in solution. So we recognize them because their formulas begin with hydrogen. Same method we used to identify them in Chapter 5. Some information about acids. Acids tend to have a sour taste. My kids love Sour Patch Kids and other sour gummy snacks. I think they're nasty, but the kids love them. The reason they taste sour is they have tartaric acid on the outside, and that's where you get that biting, sour taste. A lot of the foods that we eat are somewhat acidic, and it doesn't hurt us at all. But acids taste sour, and acids can dissolve many metals, not all of them, but they can dissolve some metals. And then bases, bless you. Bases tend to form hydroxide ions in solution. The ones we're going to deal mostly with are metal hydroxides, things like sodium hydroxide, lithium hydroxide. Bases taste bitter. Bitter is not a taste that most people like. And there's a good reason for this. Eating bases is not good for your health. Bases and human flesh do not get along well. So the bitter taste of things containing bases is a warning. Don't eat that. Bases feel slippery. I think I mentioned that to you in a lab we did with sodium hydroxide. I said if you get it on your skin, it's going to feel slippery because it makes a soap solution with your body oils, and then after a while it starts to dissolve your skin. So that's kind of gross. But that's bases. We're going to recognize bases because they are metal hydroxides. Here's a table from your textbook showing some common acids and bases. There are more, but these are the most common ones. If we look at these acids, oh, there's my iPad going crazy again. What we can see is that in their formulas, they all start with H. In their names, they all end with the word acid. So identifying these as acids should be pretty straightforward. The bases are all a metal with hydroxide. And when we look at their formulas, we see the first element is a metal, and then the second ion is OH. And that's how we identify bases. So acid-base reactions are also called neutralization reactions, and they involve an acid reacting with a base. The result of that is that water is formed. So here we have an acid, which we can recognize because it starts with H. Here we have a base, a metal with hydroxide. There are other bases, but those are the ones we're going to deal with. And when they react, they form water and salt. Here it is sodium chloride, which is the salt that we're used to calling salt, table salt. But for a chemist, salt refers to any ionic compound. Most of these are going to be soluble ionic compounds, but a salt is an ionic compound. And every time I say a salt, I think of this. This is a salt rifle. Wow. Nice. It's a rifle made out of salt. I just love that one. Okay. So the basic pattern of the acid-base reaction is this. You have an acid plus a base, and it produces water and salts. Now, you could write it base first and then acid. It doesn't matter. It's adding, and so just like 1 plus 2 or 2 plus 1 is the same answer. Whether you put one first or the other, it doesn't matter. What matters is that your reactants are on the left side of the arrow, your products are on the right side. And what we'll find is that the net ionic equation for many acid-base reactions is the same. And it's going to end up to be hydrogen ion plus hydroxide ion yielding water, which is a liquid. So Let's do an example. Let's write a molecular and a net ionic equation for the reaction that occurs between aqueous H2SO4 and aqueous KOH. So this one is sulfuric acid, and this one is potassium hydroxide. So those are the reactants, so we'll write those guys down. We've got H2SO4, writing with the eraser. That never goes well. H2SO4, and we're told that it's aqueous, and it's reacting with potassium hydroxide, and we're also told that that's aqueous. And then this is going to form something. So the way we're going to predict the products is we're going to look at the ions, and just like we did with the precipitation reaction, we're going to have the ions switch partners, and then we'll just see what happens. So in sulfuric acid, there are two ions. There's H+, and there's sulfate. And potassium hydroxide also contains two ions, potassium and hydroxide. Every ionic compound that we're going to run into in this class has only two ions. One's positive, one is negative. And so now what we're going to do is we're going to swap partners. Hydrogen came in with sulfate. We're going to see how hydrogen gets along with hydroxide. So we're going to put hydrogen with hydroxide, and we're going to put the potassium with the sulfate. So over here on the right, I'm just going to write them in their new orders. It doesn't matter which one you put first. We could put the potassium and sulfate first, or the hydrogen and the hydroxide first. I'm going to do potassium just to be different. So we've got potassium and sulfate, and then we have hydrogen and hydroxide. By writing the formulas for the ions with their charges, you're setting yourself up for success in writing the formula for the compound, because you have to consider the charges on the ions. So we look at these two. We've got +1 and -2, not the same. We can do the crisscross thing. And so that's going to end up being K2SO4. Bless you. That one's going to be aqueous. Usually the salts that form in neutralization reactions are going to be aqueous, but you could also check in by looking at the rules for solubilities. So potassium salts are always soluble. And then here we have +1 and -1, and if we just shove those together, we get HOH, and that looks a little strange, doesn't it? Like, what? Well, what if we put the two H's together instead? Let's get rid of that. What if we wrote H2O? Ah, that looks a little better. What is the physical state of water at room temperature? It's a liquid. So now I have the formulas for my reactants and products. I need to balance the equation. So let's look at this. We saw that sulfate remained as a sulfate ion. So it didn't change. We can balance it as a unit. There's one sulfate here. There's one sulfate there. Potassium. There's one potassium on the left. There's two potassiums on the right. So I need to put a coefficient in front of the KOH to make there two Ks on the left. I can't change the subscripts. And now let's deal with the hydrogens. Here I've got two hydrogens, and now I've got two hydrogens there. That's 4. Over here I only have 2. So we need to put a 2 in front of H2O to balance the hydrogens. And then I'm going to look at my oxygens. I've got 2 oxygens that are not in sulfate here, and I've got 2 oxygens that aren't in the sulfate over here. If you want to look at all of the oxygens, you can. It'll come out the same. Here we've got 4 plus 2 is 6, and 4 plus 2 is 6. So that's my molecular equation for this neutralization reaction. Any questions? Yes?
The molecular equation is balanced?
The molecular equation, well, all of the equations should be balanced. The molecular equation shows each of the reactants and products as a neutral substance. You're not going to see any charges, pluses or minuses, in the molecular equation. You're going to see compound formulas or element formulas. Any other questions? So to make a net ionic equation, we have to at least do some scribbling of a complete ionic equation to see what's going on. And our little notes that we made for ourselves here are going to help us in that. We want to separate anything that has AQ as its subscript into individual ions. And so H2SO4 needs to be separated into ions. Here we have the formulas already. We just have to look at how many of them do we have. We have 2 hydrogens and 1 sulfate. Let's start with the 2. So we've got 2 H pluses, and we have 1 sulfate. And then KOH, do we separate that into ions? Yeah, it's got AQ as its state symbol. So there are 2 potassiums and 2 hydroxide ions. So 2K plus 2 OH minus. How about K2SO4? Do we separate that into ions? Yes, we do. So in this formula, there's 2 Ks and 1 SO4. 2K plus SO4. Do we separate the water into ions? No. Its state symbol is L. Gas, liquid, solid, leave it alone. Just copy it down the same way that it was up there. So 2H2O. Check to make sure it's still balanced. So here's H plus. There's 2 hydrogens, and there's 2 hydrogens in here. That's 4. And over here I've got 4 hydrogens. 2 Ks and 2 Ks. 1 S and 1 S. This time I'm doing it separate just for grins. 4 oxygens and 2 oxygens is 6. 4 and 2 is 6. So everything's still balanced. That's a complete ionic equation. Now we look at it and decide who didn't change. Did H plus change? Does he show up as one of the products? He doesn't show up as a product, so H plus changed. That's not a spectator ion. How about sulfate? Sulfate is a spectator because he's the same on both sides of the arrow. He came and watched, didn't participate. What about potassium? Also a spectator. I'm going to cross those guys off. Hydroxide, not present on the right side, so he is not a spectator. This is a little bit like if you had something like 2 plus A plus C is equal to 2 plus F plus C. You could simplify that mathematical equation, right? If you subtract 2 from both sides, those 2's are going to go away. If you subtract C from both sides, the C's are going to go away, and you're going to end up with A is equal to F. Not sure why you'd want to do that, but there it is. If that didn't make sense, don't worry about it. The net ionic equation is copying down the things I didn't cross out. 2H plus. It's a good touch to put the state symbols back in here. And that's forming 2H2O, and that's liquid. again, it's happened that we have coefficients of 2 in front of everything. And so we really should simplify and get rid of, we're dividing by 2 all the way across. So it's really 1 hydrogen ion plus 1 hydroxide ion forms 1 water molecule. And that is the net ionic equation that you're going to end up with for pretty much any acid-base reaction that we see in this class. So if you remember that, you can jump right to it and skip all this business in the middle. Any questions? Gas evolution reactions. So some aqueous reactions form gas as one of the products. When we talked about grade school volcanoes, we talked about the reaction between acetic acid and sodium hydrogen carbonate, vinegar and baking soda, and how it generates carbon dioxide, and that causes it to foam up and erupt out of the papier-mâché volcano. That's a gas evolution reaction. Some of these form the gas product directly. So this is an example, sulfuric acid plus lithium sulfite. That's going to form hydrogen sulfide gas, which smells horrible, and aqueous lithium sulfate. So that's forming a gas directly. Others form an intermediate product that decomposes into a gas. So hydrochloric acid and sodium hydrogen carbonate, baking soda. Those are going to swap partners. The hydrogen here and the sodium here are going to swap partners. We're going to end up with carbonic acid and sodium chloride. Carbonic acid is unstable. It's something we just have to remember. Carbonic acid is unstable, and when it decomposes, it forms water, carbon dioxide. Okay, so these came from the carbonic acid, and then the sodium chloride was, of course, still there. So these are the compounds that form gas evolution reactions. And you need to remember these. There's only 4, and so it's not that tough. And I'll also tell you, this remembering of gas evolution reactions is not a big deal, okay? You can not remember this and pass the class. If you want an A, you should try to remember this. But if you're struggling with other things, don't stew about this one. So reactions in which you have sulfides, if you get H2S, that's going to be a gas, just because I said so, basically. If you've got carbonates or bicarbonates reacting and you end up with H2CO3 as an intermediate product, we need to remember that that decomposes to carbon dioxide. If you've got sulfites or bisulfites, it's the same as hydrogen sulfite, and it ends up forming H2SO3. We need to remember that that decomposes and it forms SO2. And I'll show you a way to remember what these form. And then ammonium. If we get ammonium hydroxide as a product, that's going to decompose and form ammonia gas. Also very smelly. So how can we remember these? There's some example equations down here, example reactions, and those are nice, but let's look at this. When carbonic acid decomposes, it forms CO2. It does that by losing a water molecule. So look, CO2 and H2O, if you take those letters and put them together, you get H2CO3. This has 2 hydrogens, there's the 2 hydrogens, 1 carbon, there's the 1 carbon, and here's 3 oxygens, there's 2 here and 1 there. So when these decompose, they always lose a water molecule. The gas is what's left. So when we see the H2SO3, when we take water away from this, we lose the 2 hydrogens and we lose one of the oxygens. That's the other product, that's the gas, SO2. This one does the same thing. It's going to lose a water molecule. So if we take away the oxygen, because that's in water, and if we lose 2 of the hydrogens, we'll take away that one and 1 of these. What's left is NH3. Now I made a big old mess of this. Any questions before I fix up the slide? You see how that works? It's kind of cool, huh? So let me get rid of all that mess. So what you need to do is remember that if you see one of these as a product, it's going to decompose and form a gas. It'll do so by losing 1 water molecule. The gas that it forms is everything else that's left. So when we write equations for gas evolution reactions, we start with the skeletal equation, including the reactants and products. We're predicting products by swapping cations. We're switching partners, okay? Then this is the part that's a little different from the neutralization or the precipitation reactions. We need to recognize that these 3 compounds that we just looked at on that slide are decomposed into water and carbon dioxide, sulfur dioxide, or ammonia, respectively. And then we write the corresponding equation, and then we balance it. Let's do an example. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. How nice, they didn't give us the formulas. It's okay, we can do it. Hydrobromic acid. So the prefix hydro on this acid tells me that it's a binary acid. It doesn't have oxygen in it. It's just a bromine with a hydrogen on it. And so I know from the periodic table that the ion that bromine forms has a -1 charge. And it's going to have hydrogen because it's an acid. Hydrogen has a +1 charge. So +1, -1. The formula for that then is HBr. That's aqueous. Oops. And really, I should have written those over here because we're going to need them. And then there's potassium sulfite. So what are those 2 ions? Potassium is K+. What's sulfite? It's the light version of sulfate. SO3, and what's the charge? -2. Sulfate is SO4 2-. This is the light version. It's got 1 less oxygen, same charge. So we look at this and we see the charges are different. We'll do the crisscross thing and we get K2SO3. And that's also aqueous. Now, to predict the products, we're going to swap partners. So we're going to put potassium and bromide together, and we're going to put hydrogen and sulfite together. So over here, I'm going to have K+ with Br-, and I'm going to have H+ with SO3 2-. Based on the charges of the ions, I'm going to put them together and write molecular formulas. So I'm going to get KBr, and is that aqueous? Yeah. Potassium compounds are always aqueous. They're always soluble. And then here I've got 2 and 1. So we do the crisscross thing, and we get H2SO3. And that one should look familiar. You should look at that and say, oh, that's one of those 3 that forms a gas because it falls apart. So this one is unstable. When it decomposes, it forms water, and then whatever's left after I pull the water out. So the 2 hydrogens go to the water, and one of the oxygens goes to the water. So I've got SO2 left. It's the SO2 that is the gas. So now we have this big old scribbly mess, right? Now we're going to copy it down neatly. So HBr, really? HBr was aqueous. I'm going to leave a little space in case I need coefficients in here. K2SO3 was aqueous. And then we can't forget this guy. He's just hanging up here, not minding his own business, not bothering anybody. And then we've got H2O. What's the state of water at room temperature? Liquid. And then we've got SO2, which is a gas. Is this equation balanced? No. What jumps out at you as not being balanced? Potassium. So I've got 2 potassiums here and I only have 1 there. So I need to put a 2 in front of KBr. 2 potassiums, 2 potassiums. Then we might want to check the bromine. So here's 2 bromines. Over here, there's only 1. So I need to put a 2 in front of that. And then let's look at the rest of this. The sulfite did not stay together, right? We did an example with sulfate where the sulfate didn't get taken apart. Here, the sulfite did come apart. So we need to balance the sulfurs and the oxygens separately. So there's 1 sulfur and 1 sulfur. Over here I have 3 oxygens, and over here I have 1 plus 2, 3 oxygens. And then there's still hydrogen, 2 hydrogens, and 2 hydrogens. So it's balanced. So that is the molecular equation for the gas evolution reaction. Any questions? This is going to take some practice, isn't it? So in lab this week, we're going to do a lab where you're going to actually observe some reactions happening and write down their equations. And then we're going to do complete ionic and net ionic equations from them. And then there's also a worksheet. And so it's important to do as much of that worksheet and as much of the workup on that lab in class as possible, because then when you get confused, you can ask me and I can explain it to you. There's no way that I can explain it to everyone's satisfaction in a big lecture. It just doesn't work. So I'm going to give you this first attempt, and then we'll hammer out the details in lab.